Originally, when this project was written, I wanted to create a DQN to play fighting games, and hopefully within that I would identify human behaviors and hopefully reinforce those. However, it turns out the pipes were too difficult, so I swapped to something else, and it turns out that rock, paper, scissors is very much like a fighting game in the style of choices you make. So I switched to an LSTM, and I started training on predicting another agent's moves. This code is an LSTM using TensorFlow, originally based off of a tutorial bot. However, I had to change it a lot to get pipes working, and I tried a few other train operations, and it turns out that the ones that I tried, being Adagrad and Gradient Descent, really don't have much of a difference, so I just kept Adagrad. The size of our LSTM is just what my computer was comfortable with at 128, and our truncated back proposition changed as the troubles came up, but it was mostly we would do a length of 15. The other agents in this project are mostly Bayesian networks, playing rock, paper, scissors against each other. The first thing that I used was a standard Bayesian network. The second, an algorithm that is easy for humans to use, and the third was random input for the sake of testing. The final agent that I used was a multimodal Bayesian network, which essentially is a Bayesian network that switches its strategies based off of some sort of input or some sort of trend it finds. Results would be generated by the outputs of two agents, and then the LSTM would guess the input of one of the bots. It would only guess the input of one of the bots, so it could easily identify where the training loss came from. In order to find a good base case for our AI, I decided to look at the training loss for our AI evaluating a random agent, that being an agent that always chooses rock, paper, scissors or at random. When guessing random against any other bot, the loss would always be around 1.09. When we began having our training data look at human algorithms, that being the playground examples of never do what he just did, or do what beats what he just did, or something similar, our loss would begin to approach 0. So we are seeing what we would expect from an LSTM. When we began against standard Bayesian networks, our loss would approach 0.6, and we wouldn't seem to get much better than that. This is within range to be able to beat a Bayesian network in terms of accuracy and prediction. However, when we began evaluating against multimodal networks, our batch loss had ended up at around 1.04, only 0.05 better than when we were evaluating against a random AI. My assumption is that this is because of the constant switching in a multimodal network, and that our AI is just not complex enough to be able to evaluate that. And we can see that when certain situations when the multimodal network switches less often, its efficiency does approach that of the Bayesian network. When I first approached this problem, I thought, okay, well the answer must be to just throw more on the LSTM. Surely that will fix it, right? However, when I increased it to 256 and later 512, after waiting quite a long time, I found that it really didn't help anything at all. For example, the AI would begin to train at a loss of about 1.03 instead of 1.04. And so it appears that there may be an upper limit on the complexity that you can feed into an LSTM and have it understand what you're feeding it exactly, or find a trend in that. A potential solution would be to train multiple LSTMs to identify each of those different meta strategies, and then switch and have a macro LSTM above it switch between them, essentially changing who is working within that task. In conclusion, we can find some human patterns with our LSTM, and we can go as far as finding a Bayesian network's output with our LSTM. However, we cannot go as far as finding a